So recall last time I had mentioned if a scheme is perfectly secure, as in if it satisfies, let's say, definition 2, then it is inherently very expensive. Okay. In other words, I think we had said that the key space must be at least as large as a message space. Okay. How do we prove it? So my question is, I want to prove the following claim. So if encrypt, decrypt satisfies, let's say, definition 2, of course, together with correctness, then the key space is at least as large as the message space. Okay. Is the claim clear? What we want to prove? Okay. So here's what we'll do. So this is my message space. This is my ciphertext space. Okay. I'll take some message m0 over here. I'll take some key k in the key space. Okay. And now let me just call this m. I'm going to look at the mapping that you get when you encrypt using the key k. So this is going to give me some ciphertext c. All right. Yep. Now my question is, so I have this, everything is well defined. I picked a key k, I took some message m, and I've looked at the ciphertext that you get when you encrypt m with k. Now I'm going to decrypt c using all possible keys. Okay. So if I decrypt using k, I should get back m, right? Yeah, if I decrypt using k, I should get back m. If I decrypt using some other key k prime, I'll get some other. So this is some other k prime, I'll get some other m prime. Okay. I can do this with all possible keys. Okay. And that will give me a set of messages. That can also give me bot. Okay. So maybe for some keys, I land up outside the message space. Let's say it maps to bot. That is also possible. Right? And so I have defined this set S. This is the set of all messages such that decryption, let me call this m bar, the set of all m bar such that decryption of C with some key k bar gives you m bar. Okay, this is my set S. Okay. Now, what can I say about the size of S with respect to the size of the key space?
Less than.
Why is, so the first observation is size of S is less than equal to the size of the key space. So why is that? Some may output bot, yeah, but even if they don't output bot, for every different key, some of the multiple keys could take you back to the same message. Okay. But every distinct key is going to give you some message in the message space, or it will give you bot. Bot once you throw away. Okay. So is everyone convinced that this set S that we have defined, the size of this set is smaller than the size of the keys? right? Now, to complete my claim, I want to, let me call this theorem instead of claim. My claim, my next claim is what do I want to argue? I want to argue that M is, in fact, I want to argue that clearly S is a subset of M, right? I want to argue that it's the entire message space. Okay? Clear where we are going? How do we argue this? Yes, Cyril. If it is not, then the distribution changes. Can you be more precise?
One which corresponds to that specific side of X and one which is outside S.
Okay, wait, 1 second. So your claim is if this doesn't hold, then definition 2 is not satisfied. Okay, good. The proof sketch is if S is not equal to the message space, then there exists some message M tilde which is in M but not in S, right? And we also know that M is in the set S, right? So we also know that M belongs to the set S. How do we get this? How do we know that M belongs to set S? What property of the encryption scheme gives you this? Correctness, right? So we know that M belongs to the set S. We know M tilde does not belong to the set S. And I think now Sirat's claim is we can use M and M tilde to break the perfect one-time security. Why? What we know is the adversary knows, so let's say this was our set. Okay, this was our set S and M tilde is sitting somewhere over here. Okay, the adversary knows M, M tilde and C. Okay, yeah. Let's assume that the adversary knows M, M tilde and C. What it will do is, if it receives this ciphertext C, then it knows for sure that M was encrypted, M tilde was not encrypted. Okay? Yeah. In all other cases, let's say it just gives up. So if the ciphertext that it received is not the same as C, it just tosses a uniformly random coin. If it receives C, then it says M was encrypted, M tilde cannot be encrypted. Okay? Clear? Is the attacker clear? So proof, all that's left to prove is the probability that it wins is strictly greater than half. Okay, so I'll leave that as an exercise. So if it receives, if the CT is not equal to C, then guess randomly. If CT equals to C, then guess that M was encrypted. Okay? Yep. Is the attack clear? The attacker, again, the attacker knows M, M tilde and C. If CT, the ciphertext that it receives, is not equal to C, then it just guesses randomly. If CT is equal to C, then it guesses that M was encrypted. Oh, that is because we are starting with the assumption that there is this scheme where there exists a message M which with some key maps to C, and there is a message M tilde that's outside the set S. So let's assume that the adversary knows M, M tilde and C. Okay, all of this information is present in the description of the scheme, right? This has nothing to do with the key that was picked by the challenger. So if I give you the encryption and decryption scheme which satisfies the property that S is not equal to M, then you can find M, M tilde and C. Okay. So let's assume that the adversary knows M, M tilde and C. And now my attacker is, if CT, the ciphertext that it receives, is not equal to C, then you guess randomly. Otherwise you guess that M was encrypted.
Was C chosen randomly?
Was C? No, C was not chosen randomly.
What does C represent?
Where did we get C from? Okay, let's go back to the construction. How did we start? We started with some message M. Let's go back to the start of this proof. We started with some M. Let's say this is the first lexicographic message. Take the first lexicographic key that gives you C. That is my description of C. Okay. And now what did we do after that? We decrypted this C with all possible keys. That gave us a set S. Now the question was, is this set S the same as the message space? If it is the same, then we are done. Then we know that the size of S is less than equal to the size of the key space, and we know that M is equal to S. Therefore, we are done. Therefore, M is smaller than equal to the size of the key space. If not, then you already started off with some M, which was the first lexicographic message. You started off with, you took a key K, which is the first lexicographic key, computed C. Okay, so you have M and C. And now you know that this set S is not the same as the entire message space. So there is some message M tilde that's outside this set S. So you have M, M tilde and C. Okay? Clear, everyone? Questions? This is fine. So what have we shown? We've shown that if the scheme satisfies definition 2 and correctness, then the key space has to be larger than the message space. It's easier to make this argument if you started with definition 1. I'll leave that as an exercise. Any questions before we move on? Everyone comfortable with this? Yes. Okay, so one thing that you might ask is, are we being too stringent in definitions 1 and 2? Okay, so let's look at definition 2. Suppose I relax definition 2 and I say, okay, the winning probability doesn't need to be exactly equal to half. Let's say it's at most half plus epsilon for some small epsilon. Okay, so I'll call that epsilon perfect correctness or epsilon perfect security if the probability of the adversary winning is at most half plus epsilon. Okay, maybe I can write it. So now I'm looking at a relaxed. I want to overcome this requirement. Okay, if you want perfect secrecy, then the key space has to be large. Okay, so now the question is, can we relax definition 2 and maybe reduce the key space substantially? Okay, and looking ahead, why do we want to do this? Because you want to encrypt gigabytes of data, but you don't want to use gigabytes long keys, right? You want to use short keys. The key size should not grow with the size of the message that you're encrypting. Okay, so let's look at a relaxed definition. Where I'm saying that this satisfies epsilon perfect one-time security if this probability is at most half plus epsilon. Okay, is the definition clear? All that I've done is I've said now the adversary doesn't need to win with probability half. It can win with probability at most half plus epsilon. Okay. All right. So this brings me to the main exercise from today's lecture. Unfortunately, this relaxation is not very helpful. Okay. So I'll leave this as an exercise. So you do get some saving, but not very significant saving. Okay. So what you can show is the key space is still, you get some saving, but not much. Okay. So I want you to figure out what is this constant over here that depends on epsilon. Okay. So it's some function of epsilon. Is the question clear? Yeah. Okay. So clearly, winning. If you even if you relax the winning condition, you don't gain a lot. What do you want to do if you want practical encryption schemes? So the question is, I want to get a scheme where, let's say, your key space is only 128 bits, but you're able to encrypt it using, you're able to encrypt gigabytes of messages using a 128 bit key. Clearly, that's not possible with perfect security. That's not possible even with epsilon perfect security for any epsilon. Okay. So now my question is, how do we relax the definition to further to get practical schemes? So we'll take this up in the next lecture. I'll just conclude this lecture with a quick summary of the one-time pad. So one-time pad, it's great because it gives you perfect secrecy, perfect one-time secrecy. However, this comes with some limitations. The limitations are, the first limitation of the key space has to be larger than the message space, and this is inherent due to perfect secrecy. Okay. Another is you can only use a one-time pad, as the name suggests, you can use the one-time pad only once. Okay. So another limitation is for each new encryption, a fresh key must be used. Okay. Because one-time pad only guarantees security if you pick a uniformly random key each time. If you start repeating the keys, then the adversary can learn some information about the underlying messages. What can the adversary learn if it sees, let's say, encryption of M0 and M1 using the same key? Yeah, if you give a one-time pad encryption of M0 and a one-time pad encryption of M1 using the same key, even if the adversary does not know anything about the key, it can still figure out M0s or M1. Right? Now, I think last time there was a question, okay, why do we really care about, maybe it's okay if you reveal M0s or M1. It turns out that there have been real world attacks where this was exploited, and the classic example is during the Cold War. The Russians were using some sort of one-time pad, but they were reusing keys, and the Americans collected sufficiently many ciphertexts, and over 40 years they were able to figure out some patterns and break the encryptions. Okay, so this is now declassified. It's called Venona project. Let me get the name right. Venona. Yeah. So look into this. So the moral of the story is, you want to start with as strong a definition as possible. From these abstract scenarios, it may look like, okay, well, how does it matter if we lose one bit of information? But if you accumulate that information, then there's enough to break crypto systems. Okay.
Last example, the adversary does not know that